Hello everyone. In this video, we are going to discuss resampling methods in computational statistics. And we will start by understanding why we need these methods, and then we will talk about some of the most commonly used resampling methods in this context. This is the reading list. It's chapter 5 of that ISLR textbook. There is a bit of math there, but it also does a good job of talking about the intuition. So I would strongly encourage you to read this chapter to understand more about this topic. So the fundamental challenge that we face in statistics and machine learning is evaluation. We build models to make predictions on new unseen data, but how do we know if they're performing well? That is the fundamental problem of evaluation. Think about it in this way. So when we train the model, it only sees the training data. It's like a student who has only studied certain practice problems, but the real test comes when they face new problems that they haven't seen before. If we evaluate our model only on the training data, we get what's called an optimistically biased result. The model has already seen these examples, so of course it's going to perform well on them. This is like a student who has memorized all the answers instead of truly understanding the material. They might ace a test with questions they have seen before, but they will probably struggle when the questions are new. What we really want to know is how well will our model generalize to future data, and resampling method helps us understand this critical question. So why do resampling methods matter in computational statistics? Traditional statistical methods often rely on strong assumptions about our data, assumptions that may not hold in real-world situations. For example, many traditional methods assume normality of error distribution, that our errors follow a nice bell curve, independence of observations, which means that data points don't influence each other, or homoscedasticity, that means constant variance across all values. But truth is, real world data is often messy, and it often doesn't follow these perfect theoretical patterns. And this is where resampling methods shine. They provide data-driven alternatives that make fewer assumptions about the underlying distributions. They are more robust when working with real-world data, and they can be even effective even with small sample sizes. Resampling methods help us understand critical questions like how reliable our parameter estimates are, how will our model perform on new data, and which model is optimal for our specific problem. By using the data itself to assess uncertainty and performance, we get more realistic evaluations of our model. So now let's talk about the key resampling approaches that we will explore in this course. These generally fall into two main categories: cross-validation methods and bootstrapping methods. Cross-validation methods include techniques like simple train test splits, k-fold cross-validation, and leave one out cross-validation, or LUCV. The primary goal of cross-validation is to estimate how well our model performs on unseen data and helps us select the model that is best in terms of complexity. It is about finding that sweet spot where our model generalizes well without overfitting. Bootstrap methods, on the other hand, involve sampling with replacement to create multiple resampled datasets. This approach focuses on quantifying parameter uncertainty and constructing confidence intervals. The bootstrap helps us understand the variability in our estimations. Both approaches are computational techniques that leverage the power of modern computers to perform analysis that would have been impractical in the past. Throughout this course, we will implement these methods in R, and show you how they help us build models that generalizes well to new data. In the next section, we will dive deeper into the train test split, which is the simplest form of cross-validation. So let's make the concept of train test splits more intuitive through some simple analogies. Think about studying for an exam. Your textbook is your training data. It is what you use to learn the materials. The exam questions represent your test data, new problems that evaluate how well you have understood the concepts. The goal is not to memorize the textbook, but to understand the underlying principles so that you can apply them to new situations. Or you can consider cooking. So when you practice recipes at home, that is your training data. But when you enter a cooking competition with surprise ingredients, that is your test data. You need to have learned general cooking principles, not just specific recipes. The key concept here is generalization. We are not interested in models that can simply memorize specific examples. We want models that capture the underlying patterns in the data and can perform well in situations that they haven't seen before. That is why we split our data into training and testing sets to simulate this real-world scenario where our model will eventually face new unseen data. So now let's clarify what we mean by training error and testing error, as these are fundamental concepts in model evaluation. Training error is the error measured on the same data used to train the model. It is easy to calculate. We just apply our model to the training data and see how well it performs. But that's not the whole story. Testing error is the error measured on new, previously unseen data. This is the true measure of our model's predictive performance. This captures how well the model has generalized to new situations. When we build models, we ultimately are concerned with minimizing the testing error, not the training error. The testing error tells us how our model will likely perform in the wild on new data. So why is it not enough to look at just the training error? Well, the training error is almost always optimistically biased. It gives us an overly rosy picture of our model's performance. And here's a critical insight. As model complexity increases, training error consistently decreases. The model becomes better and better at fitting the training data. But at the same time, the testing error eventually increases after a certain point. A model with zero training error might actually perform terribly on new data. This is a phenomenon that is called overfitting, and it's one of the central challenges in statistics and machine learning. When we overfit, we essentially memorize the training data instead of learning the underlying patterns. Our model picks up not just the signal in the data, but also the noise, that is, the random fluctuations that won't generalize in new situations. That is why we need methods like cross-validation to give us a more realistic picture of how our model will perform on unseen data. The difference between training error and testing error tells us something important about our model. The gap indicates how well our model generalizes to new data and whether we are overfitting the training data. A small gap means our model generalizes well. It performs similarly on both training and testing data. This suggests we have captured the underlying patterns without memorizing the noise. A large gap indicates overfitting. A model performs much better on the training data than on the testing data. That means we have created a model that is too complex, and it's one that is picking up random fluctuations in the training data that doesn't represent real-world patterns. Our ultimate goal is to find the model complexity that minimizes testing error. This usually involves striking a balance. We want a model complex enough to capture real patterns in the data, but simple enough that it doesn't start fitting the noise. So in the next section, we will discuss this balance in terms of the bias variance trade-off, which is a fundamental concept in statistical learning. But before we move on, remember, the gap between training and testing error is your first indicator of whether your model will generalize well to new data. So let's now dive into what statisticians call the bias variance trade-off, the core dilemma every model faces. When we build a statistical model, we are dealing with two opposing sources of error. First is the bias. This represents how much our model simplifies the real pattern in the data. A model with high bias makes strong assumptions about the data structure and might miss important patterns. Second, there is variance. This represents how much our model changes when trained on different data sets. A model with high variance is highly sensitive to the specific data points it sees during training. The two errors combine to form our overall prediction error. In mathematical terms, we can write this as mean squared error equals bias squared plus variance plus the irreducible error. The tricky part is that as one source of error decreases, the other typically increases. As we make our models more complex, bias tends to decrease, but variance increases. This is the fundamental trade-off in statistical learning. The optimal model is one that balances both sources of error, finding that sweet spot where the total error is minimized. So let's take a look at this graph that illustrates the typical bias variance scenario. This visualization really helps us understand what happens as we increase model complexity. The horizontal axis shows model complexity from simpler models on the left to more complex models on the right. The vertical axis shows prediction error. Notice the two curves over here. The blue line represents training error and the red line represents testing error. As we move from left to right and increase the model complexity, the blue line consistently decreases, which means the model is getting better and better at fitting the training data. The test error, which is the red line over here, it initially decreases but then starts to increase after a certain point. On the left side, we have models with high bias and low variance. These are simple models that make strong assumptions. On the right side, we have models with low bias but high variance. These are complex models that are potentially highly sensitive to training data. The sweet spot where the test error is minimized is somewhere in the middle. This represents the optimal complexity for our model. Complex enough to capture the underlying patterns, but not so complex that it starts fitting the noise. This U-shaped test error is a visual representation of the bias variance trade-off. Let's think about finding the sweet spot in the bias variance trade-off. This table summarizes what happens with different levels of model complexity. When our model is too simple, it has high bias but low variance. It is consistently wrong in the same way, and it misses important patterns and underfits the data. When our model is too complex, it has low bias but high variance. It can fit the training data extremely well, but it's capturing noise along the way as well, and those noise are just random stuff that has nothing to do with the general patterns of the data. And this leads to overfitting. The goal is to find a model with moderate bias and moderate variance, a model that is just right for our data. For regression problems, we try to minimize the expected mean square error on the test data, which we write as MSE test equals expected value of the square of the difference between our observed dependent variable and our fitted model. And this error can be decomposed into three parts: the squared bias of our model, the variance of our model, and an irreducible error, the noise in the data that no model can predict. By understanding this decomposition, we can make informed choices about model complexity rather than trying to fit different approaches blindly. So now let's talk about the simplest approach to estimating test error, the validation set approach. The idea is very straightforward. We randomly fit our available data into two parts, the training set and a validation set. Typically, we might use 70 to 80% of our data for training and reserve the remaining 20 to 30% for validation. The process is simple. We fit our model using only the training set. We then evaluate the model's performance on the validation set. We use this validation error as our estimate of the test error, how the model would perform on a completely new data. This approach is easy to implement and understand. It gives us a way to simulate what happens when our model encounters new data without waiting for actual new data to arrive. The validation error provides a more realistic picture of model performance than the training error. It helps us select models and tune hyperparameters based on how well they are likely to generalize. In the next section, we will look at an example of this approach and discuss its limitations, which will lead us to more sophisticated resampling methods like cross-validation. So think of this simple example. Imagine we have a data set with 100 patient records and we are trying to predict diabetes risk based on patient data. Following the validation set approach, we will randomly split our data into two parts. We will have 70 records for training our model and 30 records for validation. We train a logistic model using only those 70 patients in our training set. Then we test the model's prediction on the remaining 30% of remaining 30 patients in our validation set. Let's say, and this is something that we will cover soon, and this is a question of classification. Let's say our result shows a 25% misclassification rate on the validation set. This gives us an estimate that our model will have about 25% error rate when applied to new patients that weren't part of the original dataset. The validation approach gives us a much more realistic picture of model performance than we would have had if we just calculated the same error rate on the training data. While validation set approach is straightforward, it has some important limitations that we need to be aware of. First, there is high variability in the results depending on which specific split we use. If we randomly split our data differently, we might get very different error estimates. This can lead to different conclusions about which model performs best, making our model selection process somewhat unstable. Second, the validation set approach uses data inefficiently. When we set aside, say, 30% of our data for validation, we are training our model on a reduced data set, only 70% of the available data. This means our model performance could potentially be better if we had used all the data for the training. Because of this reduced training set size, validation error tends to overestimate the true test error. When we eventually train our final model on all the data, it will likely perform better than our validation estimate suggests. These limitations motivate the development of more sophisticated approaches like cross-validation, which we will discuss next. Let's talk about an extreme form of validation called the leave one out cross validation, or the LUCV for short. In LUCV, we take the validation concept to its limit. We train our data, like our training data consists of n minus 1 observations, where we have n is the total sample size, and our testing data is just one single observation. And here's the process. For every observation I in our data set, we train the model using all data except that particular observation. We test the model on that single held out observation I, and we calculate the prediction error for that observation. We repeat this process for all observations in our data set, and our final estimate is the average error across all n iterations. The key advantage here is that we maximize the training data. Using n-1 observations for each model, we give our model nearly as much data to learn from as if we used the entire dataset. LUCV is essentially running n different models to get our error estimates. It is thorough, but as we will see, it does come with some of its own challenges. Here's a schematic that helps us visualize how LUCV works. At the top, we have our original dataset with n observations labeled 1 through n. The LUCV process then creates n different training testing splits. In the first iteration, observation 1, observation 1, as shown in orange, is held out as the test set, while observations 2 through n, shown in blue, form the training set. In the second iteration, observation 2 is held out as the test set, while observations 1, 3, 4, 5 up to n form the training set. This pattern continues for all observations. By the last iteration, observation n is held out as the test set, while observations 1 through n-1 form the training set. For each of these iterations, we train a model on the blue observations and test it on the single orange observation. We calculate the error for that single test observation and then average out all the n errors to get our overall estimate. This approach ensures that every observation gets used exactly once as test case and that n-1 times as a part of the training data. It is an exhaustive approach to model validation that makes most of our available data. But it has its share of pros and cons. On the positive side, the LUCV gives us a nearly unbiased estimate of test error. There is no randomness in how we split our data. We use every possible training testing split combination, which means that we get the same result every single time, and it's completely deterministic. Another advantage for linear models specifically is that there's an actually computationally efficient shortcut where we don't actually need to fit in separate models. However, LUCV does have some important limitations. For large data sets, like data sets with millions of observations, it can be computationally intensive since we are training n different models. So if you have a data set with a million observations, you will need to run a million different regressions to implement this step, and that can be exhaustive. LUCV also tends to have high variance in its error estimates. This is because the models from each iterations are highly correlated. They are all trained on almost the same data, differing by just one observation. This means LUCV might not shake up the data enough to give us a more stable error estimate. And these limitations lead us to k-fold cross-validation, where k is less than n, and typically we use values like 5 or 10. And this gives us a better balance between the bias variance trade-offs in our error estimates. So, at the core, the problem that we are trying to solve is we need to estimate the test error, But simply splitting the data once into training and validation has its drawbacks. It wastes valuable training data, and it produces unstable estimates that can potentially depend on the specific split that we have chosen. Cross-validation offers a better solution. The basic idea is that we divide our data into k roughly equal parts called folds. We use each part as a validation set exactly once. Each time we train on the remaining k minus 1 parts, and finally we average the results over all k iterations. This approach makes more efficient use of our available data. Each observation is used for both training and testing, and it gives us a more stable estimate of the test error since we are averaging across multiple different splits. Cross-validation represents a middle ground between a single validation set, which is simple but potentially unstable, and a low-CV method, which uses data efficiently but has potentially high variance. It gives us the benefits of both approaches while minimizing their drawbacks. So the basic of this algorithm is pretty straightforward. We divide our data, that is the total observations that we have, into k folds again. Now it doesn't have to be the case that all folds have equal number of observations, but as close to equal as possible. We use fold k as our training validation set. We train our models on the remaining k minus 1 folds and then compute the error metric, which is in this case a mean square error on the validation fold. Our final CV or cross-validation estimate is simply the average across all these validation errors. This approach gives us k different estimates of test error, which we combine into a single estimate. By using multiple different training and validation sets, we get a more robust assessment of how our model will perform on new data. The parameter k controls the trade-off between bias and variance in our error estimate, as well as the computational cost of the procedure. While implementing k-fold cross-validation, we need to choose a value of k. The most common practice is choosing k equals 5 or 10. This method has several advantages over low-CV. It is computationally more efficient, requiring only k model fits instead of n. The validation set has less correlation with each other, and it often provides the most accurate test error estimates. But there are important trade-offs to keep in mind as well. If k is too small, we get higher bias than our test error estimates. If k is too large, we get higher variance similar to low-CV. Typically, keeping k around 5 or 10 provides a good balance between these extremes. But ultimately, the right choice of k depends on your specific data set, the complexity of your model, and your computation constraints. K-fold cross-validation has two main practical applications that we use regularly in statistical modeling. First, we use it for estimating the absolute test error, answering the question, how well will our model perform on new data? This gives us a realistic expectation of model performance. Second, and perhaps more importantly, we use it for model selection, answering which model will minimize test error. This helps us choose between different model approaches or select the optimal hyperparameters. For model selection, what we care about most is finding the location of that minimum error, not necessarily getting the perfect estimate of the absolute error. Even if cross-validation sometimes underestimates the true test error, it is still reliable for comparing different models and identifying one that generalizes the best. K-fold CV tends to be more stable than simple validation set approach, as we discussed earlier. Small changes in the data don't lead to drastically different conclusions about which model is the best. Another advantage is in its versatility. K-fold CV works with virtually any statistical learning method, from simple linear regressions to more complex neural networks. It is a tool that you will use throughout your career in data science. So far, we have focused on cross-validation as a way to estimate prediction error. We have looked at the question of how well our model will generalize to new data. But sometimes we have a different goal. We want to quantify the parameter uncertainty because we are interested in how would our model parameters vary if we had sampled a different data, or what is the standard error of our coefficient estimates, or how confident are we with our parameter values. This is where Bootstrap comes into play. While both cross-validation and Bootstrap are resampling methods, they answer different questions. Cross-validation helps us assess predictive performance by repeatedly splitting the data into training and testing sets. Bootstrap, on the other hand, helps us assess parameter uncertainty by repeatedly sampling from our data with replacement. Think of it in this way. Cross-validation focuses on model predictions, while Bootstrap focuses on model parameters. Both are valuable tools in our statistical toolkit, but they serve different purposes. The bootstrap is an elegant technique based on a key insight. We can use our sample as a stand-in for the population. We start with our original data set containing n observations. We create new data sets called bootstrap samples by sampling n observations with replacement. Each bootstrap sample has the same size as our original data. Some observations will appear multiple times in each sample while others won't appear at all. And then we calculate the statistic of interest in each bootstrap sample. By analyzing the distribution of these bootstrap statistics, we can estimate things like standard errors and confidence intervals without making strong distributional assumptions. The bootstrap is named after the phrase pulling yourself up by your bootstraps. The idea that you are creating something from yourself. We are using the sample to learn more about the sampling distribution without collecting additional data. This technique has kind of revolutionized statistical inference by providing computational approaches to problems that were previously solved using mathematical approximations that often relied on restrictive assumptions. Let's take a look at this simple example. Imagine we have a tiny data set with just 5 observations and we call them A, B, C, D, and E. While our original data consists of 5 observations, we now create 3 bootstrap samples by sampling with replacement. The first sample has A, B, A, E, C. So A comes in more than once. We have a second bootstrap with sample because we are drawing at random with replacement. We have C, A, E, B, D, and we have the third bootstrap sample B, D, A, C, B. Notice that in sample 1, observation A appears twice, while observation D doesn't appear at all. This is the nature of sampling with replacement. Some observations will get selected multiple times, others not at all. For each of these samples, we calculate our statistic of interest. For example, if you're interested in mean, we calculate the mean of each bootstrap sample. The distribution of these means across many bootstrap samples approximates the sampling distribution of the mean. The standard deviation estimates the standard error of our original sample mean. This gives us a way to quantify uncertainty without making assumptions about the underlying distribution of our data. It is an incredibly powerful and versatile technique that works for almost any statistic and not just means. Let's explore more with another example, probably a more realistic one, where we're looking at the stock returns data. Imagine we have a sample of 5 days of stock returns ranging from -1 to 1.5%. So in the first day it was -1%, then it was +2, +1, -0.5, and +1.5. A natural question is, what is the standard error of the mean return? In other words, how precise is our estimate of average daily return? In order to do this, we first draw 5 returns with replacement from our original sample. We might get something like plus 1, plus 2, plus 1, plus 2, minus 1. We calculate the mean of this bootstrap sample, which is 1%, and we repeat steps 1 and 2 many times, typically 1000 or more, and finally examine the distribution of these bootstrap means. The standard deviation of our bootstrap means gives us an estimate of the standard error. It tells us how much our sample mean might vary if we had collected a different sample of 5 days of returns. The beauty of Bootstrap is in its simplicity and flexibility. We need not make any assumptions about the distribution of the stock returns, which we know can be non-normal in practice. So let's wrap up by comparing Bootstrap and cross-validation side by side to understand when to use each method. The primary goal of cross-validation is to estimate prediction error, how well our model will perform to new data. Bootstrap, on the other hand, focuses on estimating parameter uncertainty, how reliable our coefficient estimates are. Cross-validation samples without replacement. When we create our folds, each observation goes into exactly one fold. Bootstrap, in contrast, samples with replacement, allowing the same observation to appear multiple times. In cross-validation, our training sets are smaller than the original data set because we have set aside some data for validation. In Bootstrap, each sample is the same size as our original data set. Cross-validation outputs an error estimate, like the MSE or classification accuracy. Bootstrap outputs a distribution of F statistics that we can analyze for standard errors or confidence intervals. We typically use cross-validation for model selection, choosing between different models or tuning any hyperparameters. We choose Bootstrap for statistical inference, quantifying uncertainty in our parameter estimates. Both methods share some important qualities. They are powerful tools that work with almost any model. They are more reliable than traditional theoretical approaches that rely on strong assumptions. And while they're computationally intensive, they are entirely feasible. They are a lot more feasible now with modern computing power. So, to summarize, what we covered today was resampling methods like cross-validation, and Bootstrap provides data-driven approaches to model evaluation and uncertainty quantification. We have seen how this works, and next we will dig into some of the R codes to understand this with actual data.